Okay, then let's get started. Good afternoon, everyone. Welcome to parallel session 13A. This is a parallel session for the subject of particle physics. So we are going to have 4 speakers, and we will have 20 minutes for each talk. And each speaker is supposed to give a talk within 15 minutes and 5 minutes for questions and transitions to the next speaker. So the first speaker is Professor Ducky Hong from Busan National University. He's going to talk about parity violation and new physics in superconductors. Go ahead, please.
Thank you for the introduction. The title of my talk is Parity Violation and the New Physics in Superconductors. This talk is based on my recent paper published last December. The outline of my talk is following. After briefly discuss parity violation in particle physics and its effect on atomic physics, I will discuss parity violation in superconductors due to weak interactions of electrons. And then with this small parity violation effect in superconductor, I will discuss how we could constrain new physics, such as Majorana neutrino or doubly charged Higgs. And then I will conclude. The parity is intrinsically broken in nature. For instance, in the beta decay of a neutron, only right-handed antineutrinos are observed. According to the standard model of particle physics, the weak interaction depends on the handedness or chirality of particles, therefore breaking intrinsically the parity. The weak interaction is of very short range because the mediated weak gauge boson is massive and at distance much larger than the Compton wavelengths of weak gauge boson, around 10 to the minus 17 meter. The weak interaction is extremely weak. So it's very difficult to see this parity violation effect at low energy. However, the atomic parity violation has been measured by many groups. The most accurate measurement was done by the Colorado group, Wood et al., published 1997. And the results agrees with the standard model by 1.5 sigma. In their experiment, they considered cesium atomic transition between 6s state to 7s state. Within QED, those transitions, dipole transition between 6s state and 7s state is forbidden because parity is conserved in QED. However, if we include the weak interaction, the dipole transition is possible, and that effect is measured. They measured the imaginary part of transition matrix element, which is around 10 to the minus 11 times electric charge times Bohr radius. And this imaginary part of this parity non-conserving matrix element is usually written as QW, which is a weak charge of atom, in this case cesium, times K, parity non-conserving, which is coming from electron wave functions and so on, over N. N is the nucleus number. And from the measurement of this transition amplitude, the extracted value for weak charge of cesium is around minus 73. This measurement of atomic parity violation places strong constraints on new physics. For instance, the sine square W of the mixing angle has been predicted by standard model in solid line here that depends on the energy. And at high energy, around 100 GeV, the collider gives very impressive agreement between experiment and theory. For instance, in Stanford linear detector or lab, it agrees quite well. Same as in electron-ion collider. However, at low energy, error is very big and there are not many measurements. So this atomic parity violation gives strong constraint. Atomic parity violation agrees with the theory by 1.5 sigma. And any new physics that modifies electron proton interaction should have a scale much bigger than 10 TeV. Similar effects can be estimated in superconductors. The low energy effective theory of electrons in metal can be described by this effective Lagrangian, where psi is electron field, and these are the covariant derivative. M star is medium mass of electron, and mu is the chemical potential. And in metal, you have massive phonons. And if we integrate them out, you get this perform interaction. Here, lambda is so-called Debye mass or phonon mass, typically around 10 TeV. And G is the coupling that characterizes the phonon exchange interaction. In the BCS theory, this phonon exchange interaction is attractive and opens the gap at the Fermi surface with the electron momentum PF and another electron near the Fermis with opposite momentum, but with the spin opposite, because the phonons does not carry any spin. So a spin singlet, a condensate is formed by the BCS theory or Cooper theorem. Here, left-handed electron means the spin is polarized along the momentum direction. So since momentum is opposite here, the spin is down to form S wave. So this electron is also left-handed. And since QED is parity invariant, right-handed electron, namely with a momentum P with a down spin, first forms a gap, and they are equal to each other. However, if we include weak gauge boson interaction, weak Z boson exchange interaction, there will be a parity breaking gap. Like this diagram, only so the left-handed and right-handed electron has different strengths with the Z boson exchange. So at low energy, Z boson exchange is approximated by this photon interaction, and this neutral current is given by this form. So as you can see, the Z boson exchange will give a chirality dependent gap. So one can calculate it to find the difference between right-handed electron gap and left-handed electron gap is given by this. Here, GF is performing coupling, and PF is Fermi momentum. Delta is the gap. VF is the Fermi velocity. And you get roughly 1.2 times 10 to minus 15 times the gap, where I use the big mixed angle to be around 0.23, and the Fermi energy is 10 electron volt. The gap is around 10 to minus 2 electron volt, which is typical normal superconductor. The weak interaction induces Hellis dependence on the Cook pair around 10 to 15, minus 15 times the gap. And this is very tiny, but which might be measurable for processes that directly depend on the gap, such as underreflected reflection. Underreflected reflection is following. So on the left-hand side, you have a normal conductor. On the right-hand side, you have a superconductor. So let's assume that the interface is around here, and the x-axis is perpendicular to the interface. So if electron comes in normal phase, then it will create phonons, and phonon will create electron-hole pair. And then electron created by phonon will make a pair with the incoming electron, and then it will form a couple pair and it will disappear in vacuum. However, the hole created by phonon will go opposite direction to preserve energy and electric charge, and also the momentum parallel to the interface. So this is the diagram that I described. The incoming electron and the hole, there will be a four-form interaction due to phonon exchange, will create electron and hole, and they form a couple pair and will disappear, creating a supercurrent phi. So this effective vortex can be calculated by using operator product expansion, and you get this expression. Here, zeta is a step function, which is 1 in the superconducting phase and 0 in the normal conducting phase. And the kappa, the strength is given by proportional to G, which is the strength of phonon exchange interaction, and the gap delta, and F is the supercurrent decay constant. So as you can see, this underleft reflection is strength is proportional to the gap. So the bigger the gap, the more underleft reflection you get. Therefore, upon the underleft reflection, electrons will get polarized. The bigger the gap, the more reflected. At each scattering, the electron will polarize roughly 10 to the minus 15. So this tiny effect is the consequence of the weak interaction parity violation. And this polarization might be measurable by spin selective underleft reflection, which was used to detect Majorana fermions in topological insulator by Stern et al. 2016. This is the schematic figure for those that experiment. So here there is topological insulator in between thin film. So Majorana zero mode are created in this topological insulator. And below there, you have SF conductor. If you apply B field in the type 2 conductor, you create a vortex. So vortex will have a magnetic field, and the Majorana particle that is polarized along the B field direction will be measured. So these are the experiments. And this kind of experiment can measure the Majorana particle. So similar to this, so this spin selective under reflection can measure this effect. But in that experiment, you don't need any topological insulate here. Just superconductor and apply this spin selective FM STM tip here. Then you may see, you may be able to measure this polarization. Now, this parity violation effect in superconductor due to weak interaction could constrain new physics such as Majorana neutrinos or double charged Higgs. So in the case of Majorana neutrino, if neutrinos are Majorana fermions, its mass will violate electron number by 2. So it contributes to the gap of the left-handed electron. So this delta is the gap, and this cross is the Majorana neutrino mass. And the wiggly line here is W gauge boson, and here is the Z boson. So if you calculate this effect, the difference is extremely small, 10 to the minus 36 times the gap for Majorana neutrino mass around 0.1 electron volt. And certain beyond standard model, such as type 2 seesaw predicts a heavy doubly charged Higgs, which will induce at low energy this kind of fermion coupling of electrons. Here, MH is the doubly charged Higgs mass, Y is the quark coupling. And this doubly charged Higgs will contribute to the gap of a left-handed electron because it couples to a left-handed electron. So this is the diagram. So if you calculate this gap, induced gap, you get roughly 10 to the minus 16 for double charged mass around 500 GeV. So suppose you measure weak interaction parity violation in the superconductor, then you get the constraint for this double charged mass should be bigger than 500 GeV. So let me conclude. So we estimate the effect of parity violation due to weak interaction on superconducting gap. And this effect is tiny, but comparable to atomic parity violation, which has been measured. So the difference in the gap between left-handed and right-handed electrons in superconductor is roughly 10 to the minus 15 times the gap. So we propose to measure this parity violating gap by using spin-selective undirected reflection, which was used in measuring Majorana fermions in Tokarev insulator. And this new effect, if measured, could test standard model at very low energy and put constraints on PASCOS new DSM physics. Thank you very much.
Okay, thank you very much for the interesting talk. So there is a question in the Q&A chat room. So I may read. I expected that chiral anomaly would be involved, but is the effect subdominant, or does the effect you focused come really from the chiral anomaly?
Chiral anomaly. No, this is Fermi slopes. This is a meta effect due to in medium. So usual chiral anomalies is not affected by having chemical potential or not. So I'm not completely sure what the question is about.
His question is whether this effect is really from chiral anomaly, or if we include the chiral anomaly effect, then it may be subdominant. Subdominant, or is the main effect?
This effect is due to parity violation of weak interaction, and yeah. I don't think it has anything to do with the chiral anomaly.
Mm-hmm. Yeah, so it should be subdominant if there is such an effect. All right. Another question. Maybe we can have one more question. So there is a question from Takahiro. For atomic parity violation, is the hydrogen atom not useful?
Yeah, I'm not the expert on atomic parity violation, but the cesium has a large weak charge because it has many nucleons inside. So, the hydrogen atom will have a smaller weak charge, and it's more difficult to measure this atomic parity violation. So I don't think hydrogen atom will be useful. But that's my guess.
Okay, thank you. Let's thank the speaker. And now, okay, let's move on to the next speaker. Next speaker is Shota Nakagawa.
Hi, can you hear me?
Yeah.
Okay, so can I share my screen?
All right.
Okay.
Okay, so Dr. Shota Nakagawa is from Tohoku University. He's going to tell us non-thermally trapped inflation due to the tachyon instability.
Okay, so thank you for introduction. My name is Shota Nakagawa. I'm a PhD student in Tohoku University. So this talk is based on the ongoing work collaborating with Pratik, Naoya, Ahmad, and Fumi. So let's get started. So first introduction, many people think the string theory as the most plausible unified theory. So string theory provides a lot of interesting implications in various fields. However, there may be some problems in string theory. So considering compactifications of the extra dimensions, the scalar fields called moduli field are copiously produced in the low energy effective theory. When the Hubble parameter is comparable to the mass of moduli, they start to oscillate around the potential minimum and behave as a matter component in the universe. So moduli easily dominate the universe soon after the oscillation. If moduli is lighter than 10 TeV, they may decay during or after Big Bang nucleosynthesis, BBN. So the radiation from its decay may destroy the synthesized light elements so that the success of BBN can be spoiled. Or even if they are stable, they can overcross the universe soon. So this is called cosmological moduli problem. There are various solutions to the moduli problem. For example, if the moduli is heavier than 10 TeV, the moduli decay is late, and so BBN bound can be cleared. Or adiabatic suppression mechanism can suppress the abundance of moduli efficiently. And also, entropy production can dilute the abundance of moduli, for example, thermal inflation. So our work is closely related with thermal inflation. So thermal inflation is a second inflation after the ordinary inflation. So there are two features of it. One is thermal trapping effect, and the other is a very flat potential. So the latter feature means that the scalar field associated with thermal inflation has a light mass and a very large vacuum expectation value. So the coupling with thermal plasma provides an effective thermal potential here to the scalar field. So this scalar field is called Flaton field. So the thermal trapping effect enables the thermal inflation to last long enough. So when the temperature is comparable to the mass of Flaton, then Flaton field is runs out of the origin and the reheating process takes place. At the reheating, entropy production, entropy is enormously produced, so this can dilute moduli abundance. Okay, what we did. So in our work, we proposed a non-thermal inflation model in a hidden abelian Higgs model with an axion coupled to dark photons. So this inflation is very similar to thermal inflation, but also distinct. So let me compare our work with thermal inflation. So thermal inflation is driven by Flaton field, which is thermally trapped by hot plasma. On the other hand, non-thermal inflation is driven by dark Higgs, which is non-thermally trapped by dark photons. Here, non-thermally means that dark photons are produced non-thermally. And also, thermal inflation requires a very flat potential. But non-thermal inflation does not. does not require such a very flat potential. It can work for an ordinary Mexican heart potential. So in our work, we numerically check our scenario by lattice simulations and investigate the possibility of solving the moduli problem, and also the experimental implications for dark photon surges. So first, let me explain the setup for this work. We consider an abelian Higgs model with an axion coupled to dark photons. The Lagrangian density is given by this. So map psi is dark Higgs, and mu is dark photon, and F mu is the field strength of a dark photon, and phi is axion. The potentials of Higgs and axion are written by these equations respectively. Higgs has an ordinary Mexican heart potential like this. So the first term in the Lagrangian includes the effective mass of Higgs. So the effective mass plays an essential role in trapping Higgs at the origin. So what is important here is that the effective mass is proportional to the dark photon field value. Thus, the Higgs acquires an effective mass from dark photon production. So the last term in the Lagrangian density is related with the dark photon production through the coupling with axions. Okay, next, let me talk about dark photon production through the coupling with axions. So the Lagrangian gives an equation of motion for massless dark photon like this form. So AK plus or AK minus represent two helicity modes of dark photon. So naively speaking, this equation has a form of the basic equations of oscillations with friction term given by the second term. So if the last term is negative or the equation has a tachyonic instability, dark photons are copiously produced. So such a situation is reliable if the axion oscillates near the potential with this relation satisfied. So in order to see this production mechanism explicitly, I want to show you this figure. So this figure shows the time evolution of the spectrum of dark photon and axion. The magenta line is a dark photon and the blue one is axion. So when the axions start to oscillate, a dark photon is copiously produced. And then when the dark photon energy density is comparable to the axion 1, tachyonic production terminates. As a result, the dark photons are exponentially produced. So in our work, we would like to use this production mechanism to trap the Higgs at the origin. Okay, next, I will explain our scenario. So we think that moduli or inflaton field dominates the early universe before the non-thermally trapped inflation. And the Higgs is trapped at the origin by haplo-induced mass as an initial condition. So when the axions start to oscillate, tachyonic production start to work, and the Higgs is tightly trapped at the origin. So when the vacuum energy of Higgs dominates the universe, the non-thermally trapped inflation occurs. After that, the dark photon field value decreases with time due to the cosmic expansions, and the tightly trapping effect is disappearing. Then the Higgs field has an non-zero effective, non-zero vacuum expectation value. And the reheating process takes place, which leads to the standard cosmology, radiation-dominated era. Okay, so based on this scenario, we can get numerical results by lattice simulations. The left panel is the field value of these particles as a function of time. So parameters are taken like this. So here we choose parameters so that inflation ends very soon. So the red, green, and blue lines represent the field value of axion, dark photon, and Higgs, respectively. So when the axion starts to oscillate, dark photon is copiously produced, and the Higgs is trapped at the origin. And then, when the trapping effect disappearing, the dark Higgs has a non-zero wave, as I explained in the previous slide. So the right panel is the equation of state for total components in the universe. So in the early universe, W equals 0, or matter domination. And then W becomes smaller than minus 1/3, which means that the inflation, non-thermal inflation occurs. So anyway, we can check the validity of our scenario by lattice simulation like this. So next, let me show the possible parameter space and the contours of the e-folding number. So in this figure, the horizontal line is the axion mass, and the vertical line is the vacuum expectation value of Higgs. The dot-dashed blue lines represent the contours of the e-folding number, n equals 5 and 10. The gray shaded region represents the BBN bound, and the green one is the region where the inflation does not occur. And in the orange shaded region, Higgs is not trapped before tachyonic production, so we are interested in the white triangle region here. So importantly and interestingly, our scenario is applicable to an ordinary Mexican hat potential with lambda equal 1. So which means that the very flat potential is not required. So this is important aspects of our scenario, of our work. And also, in the region surrounded by red dashed lines, a moduli problem can be solved or relaxed. Okay, so finally, let me discuss the reheating process and the experimental implications. So we assume the kinetic mixing between U1Y gauge boson and dark photons, which can be described by this Lagrangian. So epsilon is a kinetic mixing parameter. So in this case, dark photon can dominantly decay into electron-positron pair. So then the reheating temperature can be computed like this. So these reheating temperature are the cases that the decay rate is lower or higher than the Hubble parameter at the end of inflation. So anyway, reheating temperature is about GeV scale for these reference values. So using this reheating temperature to estimate some bounds, we can get this figure. So the horizontal line is dark photon mass, and the vertical line is a kinetic mixing parameter. The gray shaded region is the region where our scenario cannot work. So BBN bound, and here is Higgs not trapped before tachyonic production. And also colored solid lines here represent the current bounds by experiments. So white region is still alive here. And the colored dashed line represents the future sensitivity by experiment. And black dotted line denotes the contours of reheating temperature. So for these parameters, the reheating temperature is from 10 MeV to 1 GB. So interestingly, the origin of the universe or reheating process can be investigated by the terrestrial experiment, such as HPS or LCB and SHIP and so on. So to summarize, in our work, we propose non-summary trapped inflation in a hidden abelian Higgs model with an axion coupled to the photons. So very strong non-thermal trapping enables a large entropy to be produced even in an ordinary Mexican hot potential. We confirm that the non-thermal inflation occurs by lattice simulations. So our scenario predicts the photons which can be searched for by future collider or fixed target experiments. Thank you for your attention. Thank you.
Okay, thank you for the nice talk. So we have a question from Takahiro. It may depend on the parameter, but what happens if the dark Higgs initially breaks the U1 and the dark photon becomes heavy before the axion oscillates?
Oh, that's a good question. So if the U1 is broken at the first time, so Higgs has so dark photon has a mass. So tachyonic production mechanism does not work so much. So, so we consider the trapping. We consider the trapping effect by the Ritchie-Scalar coupling. Okay.
Okay, so another question is from Kwangshik. Dark photons produced during axion oscillation would be thermalized with dark Higgs. If this is the case, I wonder how large thermal effects on Higgs trapping is.
Okay. So that's a good question. So, but so this coupling is higher order. So, the scattering rate is negligible, I guess. I don't know the detail, but it's negligible, I think.
So I have a related question. So we have such a large value of dark photon field, then you should give an additional potential for axion, right? And that effect is included in this simulation.
Simulation. So in this lattice simulation, we don't consider the Ritchie-Scalar.
I see. I think that backgradation effect can be important. I'm not sure, but yeah, it should be included.
So
additional axion potential from the dark photon field.
So in our lattice simulation, so lambda is very small.
What is lambda?
So self-coupling of Higgs.
I mean the axion couplings to dark photon.
Okay, I see. The axion coupling. I'm not sure. So.
Okay, yeah. Let's see. Okay, so let's thank the speaker.
Thank you.
Now let's move on to the next speaker, Dr. Yuichiro Nakai.
Hello, can you hear me?
Yeah, it's good.
So,
yeah, so the next speaker is Yuichiro Nakai from TD Lee Institute in Shanghai Jiao Tong University. He is going to tell us axion quality from superconformal dynamics.
thank you for the introduction. I will talk about the solution to the axion quality problem, which is in general problematic in the axion solution to the strong CP problem. This talk is based on the work with Moto Suzuki in TDD Institute, Shanghai. Okay. Okay, let me start with the introduction of the strong CP problem. QCD Lagrangian for strong interactions allows this kind of theta term, which is explicitly violating CP symmetry. And actually, this physical strong CP phase is a problematic, the theta bar. This is a combination of theta and the quark mass matrices. And the current upper bound on the neutron electric dipole moment strongly constrain this theta bar. And the strong CP problem asks why this theta bar is so small. This is a very mysterious question. And the most common explanation is a Peche-Quinn mechanism that strong CP phase is promoted to a dynamical variable like this. And the temperature of the universe is decreasing, then the axion potential is developed, and the axion, this A, dynamically cancels, develops the potential and cancels the strong CP phase. And the axion is introduced as a Schudnam-Goldstone boson associated with spontaneous breaking of a global U1 Peche-Quinn symmetry. And non-perturbative QCD effects break the U1 PQ symmetry explicitly and generates this kind of potential. Here, m pi is a pion mass and f pi is a pion decay constant. And so strong CP problem is solved by dynamical mechanism. And astrophysical observations put a lower limit on this parameter FA, and FA is roughly larger than 10 to 8 GeV. Okay, and next I will explain the axion quality problem. So the sufficiently small strong CP phase requires a U1 Peche-Quinn symmetry to be realized to an extraordinarily high degree. However, on the other hand, quantum gravity effects, it has been known that quantum gravity effects do not respect such a global symmetry. And in general, Planck suppressed U1 PQ violating operators are expected. So for the Peche-Quinn breaking field, phi, this kind of potential is expected. And this potential destroys the Peche-Quinn mechanism. So this kind of axion potential is additionally generated, and phi is an arbitrary phase, and the axion potential is minimized at a different place. So this destroys the axion solution to the strong CP problem. Okay, and the other approach is using superconformal dynamics to solve this axion quality problem. Okay, next, I will briefly describe our mechanism to solve this axion quality problem. So the PQ breaking field marginally couples to CFT sector fields. So here in the superpotential, the O is composed of the CFT sector fields, and phi is a PQ breaking field, and lambda is a dimensionless coupling, and this coupling is marginal. And then the PQ breaking field phi holds a large anomalous dimension. And after canonically normalizing this phi field, then this kind of suppression factor appears in front of the coupling. And this is epsilon is very small, the smaller than 1. And the U1PQ, dangerous U1PQ violating operators are significantly suppressed at low energies. So if we have this kind of a term in the superpotential at the beginning, but this epsilon, small epsilon suppression factor appears, and then this dangerous term is suppressed, and quality problem is solved. So this figure summarizes what happens in energy scales. So at this lambda, some scale lambda, the theory flows into a conformal fixed point, and there is some energy range where the theory is in the conformal fixed point. And at some scale MC or FA, PQ breaking happens. And this PQ breaking also drives the conformal breaking, and all the CFT sector fields become massive. Then we can integrate out this kind of CFT sector fields, and it generates the desired axion coupling to the gluons, which generates a correct axion potential. This is very similar to the so-called KSBZ axion model. So this is our general idea. And I now show you an explicit model based on the n=1 supersymmetric QCD. Our model is SUSY SUN gauge theory with NF vector-like quarks. These are quark flavors. And we here assume this NF is even. And the theory is in conformal window. And to solve the strong CP problem, I introduced the Pechequin singlet chiral superfields phi bar. And this phi couples to the half of the QQ bar, and phi bar couples to the other half of QQ bar. Then the flavor symmetry is like this, and color SU3C is embedded in one of these SUNF over 2 factor. Okay. And this table summarizes the charge assignments. And this Q, not Q bar, are charged under the U1PQ. And the phi bar also have charges. Of course, they have PQ charge, but their charges are opposite. Then the U1PQ symmetry is not anomalous under the new SUN. And this is important because it ensures axion does not couple to the new SUN gauge field so that no new axion potential is generated. And on the other hand, for the color SU3, the color SU3 has anomaly, and the anomaly coefficient is calculated like this. And then the ZN symmetry as a subgroup of U1PQ is an anomaly-free discrete symmetry. And we impose this discrete symmetry to ensure the U1PQ symmetry at the renormalizable level. Okay, the SUN gauge coupling G and lambda bar coupling in the superpotential enter a non-trivial IR fixed point at this lambda scale, and there's a conformal region. And MC or FA, there's a PQ breaking. And during this conformal range, the anomalous dimension of PQ breaking field phi is developed and determined by the U1R charge in supersymmetric QCD. So this is a wave function renormalization factor of phi, and gamma phi is anomalous dimension and determined like this. And we canonically normalize the phi as this phi hat, and we can get the suppression factor in front of the coupling. And here, this Pechequin breaking scale, the phi bar obtains non-zero bev. And with this superpotential, so phi and phi bar develops a bev. So as you see, all the new quarks become massive. Then we can integrate out these heavy quarks, and we get the axion coupling to gluons, and we get the correct axion potential. Okay, and so after integrating out these heavy quarks, the model becomes a SUN pure-Yang-Mills theory, and it confines. So this SUN gauge coupling is relatively strong, so it confines just below the conformal breaking scale. And so we can expect the existence of heavy SUN glue balls and their superpartners in the spectrum. Okay, let me now estimate how the axion quality is achieved in our model. The most dangerous operator respecting the ZN symmetry is given by this superpotential. But after canonical normalization of phi hat, we have this kind of suppression factor. And this gives scalar potential in supergravity with this constant term. The M3 is a gravitino mass. And I introduced here the model-dependent coefficient kappa. And so we have this kind of scalar potential. And this scalar potential develops the U1PQ violating axion potential. And here phi is arbitrary. So this may be, this is possibly dangerous. And how dangerous we estimate. So we now define the axion quality factor like this. And so I introduced this Q, and the experimental upper bound requires Q must be smaller than 10 to minus 10. And this plot shows this axion quality factor in terms of the gravitino mass and the FA, the decay constant. And here I take the NF equals 2N, MC equals FA, and the model-dependent parameter kappa is 1. And the conformal entering scale lambda is 1 order magnitude smaller than M Planck. And the solid line is Q equals minus 10, and the dashed line is Q equals minus 8. And as you see, the quality problem is solved for n equal 5, 6, 8, 7, 8, and n equal 5. For n equal 5 or larger, we can solve the problem with a reasonable gravitino mass. Okay, finally, I checked the existence of the IR fixed point for the gauge coupling G and lambda lambda bar. And this figure shows the RG flows of the gauge coupling G and the coupling, superpotential coupling lambda from this some scale lambda 0 to this scale. And I take here the n equals 5, nf equals 10, and the lambda bar equals 2 at the lambda 0. And here I ignore the effect of the color SU3 gauge coupling. And so the coupling flows with this direction. And the red is 2 loop RGEs, and the blue is the 1 loop. And in both cases, the couplings flow into a non-trivial IR fixed point, we can see. Okay, I now include the effect of the color SU3 gauge coupling. So the initial value of G lambda lambda bar is like this. And I consider the 3 cases at for the initial condition of the color gauge coupling at the lambda 0. This is the flow of the anomalous dimension at 2 loop. And this is a flow of the wave function renormalization factor inverse at 2 loop. And so these 3 curves corresponds to these 3 cases. But anyway, the anomalous dimension is flowing into the value without the QCD effect at low energies. And the anomalous dimension, the wave function minimization factor inverse is going to be very suppressed. And the smallness enables to solve the axion quality problem. Okay, let me summarize my talk. I introduced one solution to the axion quality problem, which is in general problematic in the axion solution to the strong CP problem. And here we use the superconformal dynamics to address this problem. And in a model based on the n equal 1 SQCD, Peche-Green breaking fields marginally couples to new quarks charged under the color SU3C and a new SUN gauge interaction. And due to this coupling, the large anomalous dimension of Peche-Green breaking fields is developed, and this leads to a strong suppression of the explicit U1 PQ violating operators. And the PQ breaking drives also a conformal breaking, and integrating out this heavy quark, then it generates the desired axion coupling to gluons, which is leading to the correct axion potential. Okay, that's all. Thank you very much.
Thank you for the interesting talk. So we have several minutes for questions or comments. So question from Takahiro. Doesn't quantum gravity effect breaks the ZN symmetry?
No, yeah. So this ZN symmetry, so we consider this ZN symmetry as a gauge symmetry. So I think the gauge symmetry is okay under the quantum gravity effect. So yeah. Does this answer question?
Yeah. So question from Hyunmin, yeah.
Yeah, that's the interesting direction. Yeah, so I also consider this possibility, but I have not yet done anything. But yeah, but that's very important, a very interesting direction. Yeah, so the same conformal dynamics can address the SUSY flavor problem, like Nelson-Strassler mechanism. Yeah, I think that's very interesting direction.
So maybe a naive question. What may be the most challenging part for this setup?
Sorry.
What may be the most difficult part for realizing this idea?
Difficult part.
Yeah, in solving this problem.
I think this model works well.
Works well. You think it's perfect?
Yeah, but actually, unfortunately, so we still have not yet have a concrete prediction which can be tested at some experiment observation. So yeah, we are now exploring, but so we still have not have concrete answer. So that's I don't know. Maybe most difficult part.
It's a theoretical challenge.
Yeah. But I think the mechanism itself is generically applicable. So yeah, for the axion coupling. No, it's completely same as the very similar to the case VZ case. So yeah, so how can I say, not specific to our model. So the axiom, yeah. Extra anomalies from heavy quarks. Yeah, so heavy quark anomaly gives axion coupling to the ordinary color SU3C gauge coupling. But the point is that the no axion coupling to the new SUN gauge interaction. That's a key point. And this avoids additional potential, axion potential. So yeah, maybe that's one key point in our model.
Okay. Thanks a lot. Let's thank you again.
Questions? Thank you. Bye.
And our final speaker is Kimiko Yamashita.
Hi, thank you very much. I will share the screen.
Yeah.
see the screen?
Yes. So Dr. Kimiko Yamashita is from Institute of High Energy Physics, Chinese Academy of Science. So she is going to tell us elastic positivity versus extremal positivity bounds in SMEFT. Yeah, please.
Thank you very much for your kind introduction. I'm Kimiko and collaborate with Professor Chen and Professor Xiongyeon. This is a plan of my talk. First, I will briefly introduce effective field theory and standard model effective field theory. Then I will introduce positivity bounds, and I will show the results of positivity bounds on F to the fourth operators obtained by the elastic positivity bounds and extremal positivity bound. Then I will compare these two, and I will summarize in the end. EFT is effective field theory, and heavy degrees of freedom decouple in this theory. And this theory is for large distance phenomena or small momentum scale. So EFT interaction terms are described by here. And this is dimension 5, 6, 7, 8, and so on, and suppressed by the coupling lambda. And the coefficients are named by Wilson coefficients. SMEFT or standard model effective field theory is extending the standard model by adding massive particles heavier than the energy scale of scattering. These higher dimensional operators are SU3, SU2, U11 invariant higher dimensional operators and built by standard model fields. SMEFT is one of the model-independent ways to search for new physics. So EFT is for the energy scale of the E is smaller than the cutoff lambda, so that the heavy particles are decoupled. Then many UV models correspond with EFT. Here in the EFT, Wilson coefficient can be selected by anybody. But from the general feature of UV theory, can we bound Wilson coefficients of EFT? So then the UV theory can restrict the EFT. So here, the general feature of the UV theory is the local quantum field theory. And I think that these are special relativity correspond with Lorentz invariance, and the conservation of the probability correspond with unitarity, and the causality correspond with the analysis of the scattering amplitude. So one of the ways to do this, constrain the EFT from the general feature of the UV theory is positivity bound. Positivity bound is the sign of the certain combination of Wilson coefficients in EFT have to be positive. For example, W to the fourth operators, here this W hat is a field strength constructed by the W field. So W to the fourth operator, there are these four operators. And one of the positivity bounds is here, so that the sign of the certain combination of the Wilson coefficient should be positive. This is a positivity bound. So positivity bound can apply for dimension 8 operators in 3-level SMEFT. This is because the base is on the Hroasa bound. Dimension 8 operators are more suppressed by the cutoff lambda than lower dimensional one, dimension 5 or dimension 6. However, for example, dimension 8 anomalous quartic gauge coupling operators, LHC experimentalists have been and currently working on constraining them. This is a figure, and I will show the next slide. So in the future, more dimension 8 effects may become accessible from the experiment. So here, the figure of in the previous slide, and the Wilson coefficient is constrained by the experiment from this inside the black circle. So inside this circle is excluded by the experiment. However, positivity bound is, only the inside the circle is allowed from the experiment because the Wilson coefficient is small. However, the positivity bounds allowed only the green shaded region, so that this is a very complementary bands. So positivity bands can be obtained traditionally by considering elastic forward scattering by using EFT operators. And recently, new approach for positivity bands is established, named by extremal positivity band. So comparing B with this one should be useful. To see this, we use F to the fourth operators as a concrete example. Deriving bands on F to the fourth operator itself is also useful as offering complementary bands to the experiment. F to the fourth operators in our work is this 10 operator. So this is again field strength constructed by the W field, and this is a field strength constructed by the B field. And let me introduce the dispersion relation. This is required for deriving positivity bands. And this is derived from the unitarity and analyticity feature of the UV theory. So dispersion relation is here. And this is a scattering amplitude of the ij2kl from the dimension 8 EFT operators. So that basically this is a proportion to the S square, because the dimension 8 operator is suppressed by the cutoff scale to the fourth, and the amplitude is non-dimension and dimensionless for the 2-2 scattering. And also this dispersion relation connects this EFT amplitude to the UV amplitude. Here's ij to the any UV particle. So that this dispersion relation connects the EFT amplitude and some UV theory amplitude. Then we can just relate this dispersion relation by decomposing the amplitude by the real sector and the imaginary sectors. Then if we think the elastic scattering, ij to ij, here is just ij to ij, and this is positive. Then just this right-hand side is a positive summation, so that this is EFT amplitude should be positive. This is positivity. And Wilson coefficient is constrained. And more generally, elastic forward scattering between the superposed states can be considered, so that we can think the initial state as a superposition of the fields and consider the elastic scattering of the superposition state and AB to just go to the AB for the scattering. And just the quick small calculation shows us that the right-hand side is also positive. Then here is also positive. This is a generalized elastic positivity band. By using this superposition of the elastic forward scattering, we can derive the positivity band. Here, the field is W1, W2, W3, and B. And also this is a polarization direction and the direction to the X and Y for vectors. And we can get considering this scattering. By considering this scattering, we can get a linear positivity band. For example, this is these bands are obtained by this superposition scattering. And also we can get some quadratic and cubic bands, and the parameter space is constrained to the 0.7% of the total. So that the Wilson coefficient parameter space remains only 0.7% from the theoretical point of view. So then let's move on the dispersion relation for the extremal positivity bands. For this, we can rewrite the dispersion relation by this form. This part is positive, and here is UV dynamics, and here this part is determined by the symmetry. And this one is the Krebosch-Gordon coefficient, and for this R, we can consider the SO2 low rotation of the forward scattering axis, and also standard model gauge symmetries. And because here is positive, and just a positive summation of this part is this amplitude. So that this relation is the same with this relation. These XY element are member of this set C, and this positive summation of multiply the positive number, and the summation of this is also inside this set. In this case, we call it this set the convex cone, and the convex cone is like shaped like here. So this dispersion relation tells us this amplitude should be inside this cone. So this set and the element is this amplitude should be inside the cone. And also dynamics by the SMEF determine the EFT amplitude should be the Wilson coefficient, and determined by the operators. This is some number. And so then the dynamics determines the amplitude should be the some set F determined by the operator. So the positivity bounds are obtained by the intersection of this set C determined by dispersion relation, and set S determined by the SMEF dynamics. By using this relation, we derive the positivity bound. And the WWW case, here we had an extra inequality, and this is better than the elastic positivity approach. This inequality appears first from the external positivity bound. And by using these two operators, so elastic positivity bounds only allow this purple region, but however, external positivity bounds limits more strongly. And this is a full bounds of the linear inequality, and we got this relation, and the quadratic relation we'll also get. So let me compare the elastic positivity approach and external positivity approach. And around parameter space is almost the same. However, external positive approach is slightly gives a strong constraint. And also this external positive approach is well algorithmized, because we can directly write down using the group theory as a guideline to know the edge of the cone. And the numerical calculation speed is faster for this case. Let me summarize. If the UV theory possesses unitarity and analyticity of the S matrix, the signs of certain linear combination of Wilson coefficients in EFT have to be positive. This positivity can be applied for many kinds of EFTs. And here we apply the positivity to SMEF, especially F to the fourth operators, by using elastic and new external positivity bounds. And the bounds are very strong. 99.3% of the Wilson coefficient parameter space is excluded, and give a useful guide to experimental studies. And the external positivity approach has a potential ability to apply for a more complicated case. Thank you very much.
Thank you very much for the interesting talk. Okay, we have now time for question. So, Won-san? Can you tell?
Hello, can you hear me?
Yeah.
Okay. Thank you very much for your nice talk. Actually, I'm curious about a measure, especially assuming that we are given a set of violations of positivity bound for some processes, then I'm curious if there is some optimal variable or measure to quantify the total variation of violation.
So you wondered how to quantify the positivity violation?
Yeah, actually, that violation would be measured process by process, and that should be transformed or transformed in the basis of Wilson coefficient. Then it's quite a large dimension, 7 or 8 or maybe more. Then in that case, I'm just curious. So for a set of the violating process which are related to some values of Wilson coefficient, then so is there some good framework for variables which quantify or measure the positivity bound violation? As so, for example, can you say can you say that so just by one number can you quantify the violation?
Yes. So there's a paper proposed quantify the positivity violation. Yes, actually there is. But this quantifying the positivity violation is very simple. As you said, just some deviation from the positivity.
Yes.
Yes.
That is just assuming it is just linear sum of the positivity. You mean the second derivative one for all the processes. So you mean that linear summation or?
So you mean that
yes, so maybe my question is quite ambiguous, but I'm not quite sure about your process, but I'm just imagining that there, you have the EFT frame, which consists of the Lachapelle Wilson coefficient. Then that Wilson coefficient is tested using some elastic spectrum process or some processes. Then using the measurement from that lots of processes, you get the constraint on the Wilson coefficient. Then, but there exist lots of processes, but partly there is some subset of processes which it shows that violation. Then lots of several violations for that violating processes. Maybe you can just add up that quantity to report the violation, or you might just scale the sum of them to quantify the violation. So I'm just wondering if there is a good measure for quantify that multi-dimensional violating quantities from these violating processes.
I see. So basically, I think processes are basically the same, but the Wilson coefficient is different.
Processes are same. That if so do you Okay. Maybe I'm imagining some different cases. Actually, I was imagining the test of the violation from by using many different experiment at different independent processes.
I see.
Yeah.
I see. Because the operator restricts the process itself. If the operator restricts the process itself. So well, I can only imagine just the difference is Wilson coefficient.
But isn't it more general to natural to consider the case where we constrain the Wilson coefficient from the variable, the various physical processes, or so as many as we can. For example,
this part I'm not sure yet.
Okay, I see. So, okay, thank you so much for your talk, and maybe I can ask later.
Okay.
Email communication. And we have another question from Hyunmin. You see the chat. Wilson coefficient undergo running at new physics scale. Have you taken into account the operator mixing for external positivity bounds? Are they important?
Yeah. Wilson coefficient running at the new, yes. Have you taken into account the operator mixing for external? This part, no, we didn't take into account the operator mixing for positivity bounds, including extremal positivity bound. And operator mixing. Operator mixing means that
RG mixing.
Yeah, operator mixing
means the mixing induced by RG running.
I see. This one we didn't take into account. We just use the same operator is independent.
You use tree-level value. You take into account only tree-level values. Without
yes,
running.
Yes, we only consider the tree level.
Yeah, I see.
Yeah, I think important. It's so high, that's why I asked about that. Yes, cutoff scale should be high, yes. Yeah, running should be interesting, but I cannot answer now, yeah.
Okay, then let's thank Kimiko. And yeah, so now this session is over. I'd like to thank all the speakers and participants. Now we have 30-minute breaks. See you later.